Bismillahirrahmanirrahim. In this video we are going to go through lesson 4, which is DC generators. There are 5 major types of DC generators that we are going to discuss in this lesson. They are classified according to the manner in which their magnetic field circuit is connected to be powered up, in a similar way to the DC motors that we have discussed in the previous lesson. Each of these DC generators has different terminal characteristics and therefore suitable applications. These 5 major types are: first, separately excited generator, then shunt generators, series generators, cumulative compounded generator, and differentially compounded generators. Okay, one of the most important parameters when we discuss about DC generators is what we call as the voltage regulation, which is given by the equation as shown in the slide here, that VR, or the voltage regulation, is equal to VNL minus VFL over VFL times 100%. VNL is the no load voltage, the no load output voltage, and VFL is the full load output voltage. This quantity tells us that about the variation of the output when the load changes. In ideal case, the change is 0 when the load changes from 0 to its full load. So we can say that generally when we have lower VR, it means that the generator works better with the variation of load. Okay, all generators are driven by a source of mechanical power called the prime mover. And this prime mover may include things like a steam turbine, a combustion engine, or even an electric motor. All these prime movers are those devices that will provide the mechanical power input as an input to the generator. Without this mechanical energy going into the generator, then the generator will not be able to generate electricity as its output. And this diagram shows us how this prime mover can be connected to a DC generator, and it will supply. So this is the prime mover here, and then it will supply the torque, which will then rotate this shaft here, which is connected to the DC generator. So when the prime mover rotating, the DC generator rotor will also rotate, and by this then it can generate the electricity across its output that will be supplied to the load. Okay, how about the equivalent circuit? As we learn with the DC motors, equivalent circuits are very important, and so similarly for DC generators, we'd like to use equivalent circuits as well to help us analyze the performance of these machines. And similar to DC motors, DC generators also have 2 parts in the equivalent circuit, which is shown on the left hand side here. Here is the field circuit, and on the right hand side is the armature circuit. And remember that a field circuit is the circuit that will have the field current, and this field current is the one that will generate or induce a magnetic field in the machine. And remember also that without any magnetic field, if there is a zero magnetic field, then the machine will not work, and therefore it will not be able to generate any electricity. Yeah. Okay, and again, as you can see, they are very similar. Actually, the difference is in the direction of the armature current here. Rather than going from the right to the left, rather than going from the terminal, it's actually going into the terminals. Yeah. Okay, and another thing is the polarity of the brush voltage here. So it's the opposite to the one that we saw with the DC motors. Okay, apart from those two, they are very exactly the same. Okay, and for the field circuit, again, we have two resistance here, which is the RF, which is field resistance, and adjustable R is there because in some generators we use it to be able to control the field current, and therefore we can control the magnetic field, adjust the magnetic field, and in turn this will then control the output voltage of the generator. Okay, and apart from that, we got this LF, which is the field inductance. However, in our analysis in this lesson, we are not our calculation will not be affected by this LF, and therefore we can ignore this LF. Okay, and then on the armature circuit, we have the EA, which is the internal generated voltage, or also we call it as back EMF, yeah, which is induced when the machine is rotating and magnetic field is present. Okay. And the V brush, or the brush voltage, is the voltage that drop across the brush. And remember, brush is part of the commutation system in this kind of machine that will help us to kind of convert from AC to DC, or vice versa, depending on the connection of the machine. And then RA is the armature resistance, which is the resistance that represents all the total resistance in the armature circuit. Okay, yeah, it includes the resistance of the windings, and also of all the wires connecting the windings to the terminals. Okay, now we've come to the first type of DC generators, which is separately excited. Yeah, what is a separately excited DC generator? It's a generator whose field current is supplied by a separate DC voltage source. Yeah. This is the unique characteristics of this type of DC generator. With other types of DC generator, all of them will have their field current supplied by internally. Yeah? So they are not using any separate DC voltage source or DC voltage supply. Okay, but for this type of DC generators, we do have a separate DC voltage source, which is shown here. This is our separate DC voltage source that will supply the field voltage into the field circuit, and therefore you can have the field current flowing through the circuit, and by having this, the field winding can then generate the magnetic field. Okay, yeah, and again, this is the unique characteristics of the separately excited DC generator, as its name implies. Okay, the notation that we use here, VT, is the actual voltage measured at the terminal of the generators, yeah, which is basically the output of the generator, the terminal voltage. And then you've got IL, which is the line current, which is the current flowing in the lines connected to the terminal. Yeah, this is IL. And then you've got the EA, the internal generated voltage or back EMF, and then you've got the IA, the armature current. Yeah, and yeah, all these four are on the armature circuit part of the equivalent circuit. Right, and then as we did with the DC motors, by using this equivalent circuit, we can derive the equations that we can use in the analysis of the performance of this DC generators. Okay, we start with IF, which is the field current, and as we can see, IF is flowing in the field circuit on the left hand side here of the equivalent circuit. We can simply derive that IF is equals to the voltage, which is VF, divided by the resistance, which is RF. So IF equals to VF divided by RF. Okay. Okay, next we've got internal generated voltage, which is on the armature part, armature circuit part of the equivalent circuit. This is our EA here. Okay, and we are going to use KVL, Kirchhoff voltage law. So EA will be equals to remember that the current flowing from the current is flowing what we call counterclockwise, sorry, clockwise here, and therefore it will be this voltage across RA and the voltage across VT. Yeah? The sum of these two voltages will be equal to EA. Okay, so therefore EA will be equal to VT plus plus IA RA. Right. Okay, and the final one, so is there's a mistake here. It shouldn't be IF, rather we have done IF, so it's supposed to be IA here. Yeah, which is, or probably we can do IL, which is simply equals to IA. Yeah. And again, if you look at the diagram, it's referring to this is IL and that is IA. Yeah? So the two are the same. Okay. Now we'd like to see the terminal characteristics of this type of DC generator. Remember when we talk about terminal characteristics for DC motors, it was a plot of torque against the speed, yeah? Because the output of motors are mechanical, yeah? And so we talk about torque and speed as part of the terminal characteristic or the output characteristic of the type of the motors. Now when we talk about DC generators, the output that we talk about is in terms of voltage and current. Specifically is the terminal voltage and the line current. Yeah? Right, so we want to see how the VT changes with the line current. Line current is representing actually the load. Yeah? If the load is 0, then the line current will also be 0. If the load is high, then the IL or line current will also be high. Yeah? So again, what we'd like to see here, how VT, or the output voltage of the generator, changes when the load changes. Okay, when we discuss about these terminal characteristics, we should assume that the speed of the motor is, or of the generator, is constant. Yeah? So the speed is constant. Yeah, you can use omega m or nm depending on what unit you are using. Is it radian per second or revolution per minute? Right. So from the KVL, we did find that EA equals to VT plus IA RA. And if we rearrange the equation, we can find that VT is equals to EA minus IA RA. Okay. So EA itself is equals to K pi omega m. Yeah, we learned about this before, and we know that omega m is constant, K is also constant. How about pi, or the flux in the system? Flux is a function of mmf, which is function of the field current. Okay, the field current is flowing in the field circuit of the equivalent circuit, and therefore it's not actually affected by the change in the load, by the changes in the IL. Okay, so it means that the flux is also constant, and therefore EA is constant, and this is what it means by this, the first statement in the bullet point, yeah? the first bullet point statement. Right. Okay, and then the second one, when the load supplied by the generator is increased, yeah, IL and IA is also increased. Yeah. So when the load is increased, we know that load is proportional to IL. Again, I already mentioned before that when the load is 0, IL will also be 0. Yeah? So when the load is increased, IL will also be increased, and IA will also be increased because IL is equal to IA. We can quickly have a look again. Here you can see that IL is equal to IA, and therefore when IL is increased, IA will also be increased. Yeah? And as the IA is increased, yeah, the voltage drop IARA also increase. So we are talking here, if you could see on the right hand side here, this IARA, yeah, the voltage drop also increase, which means that the difference between VT and EA is getting bigger. Yeah? Yeah? And therefore actually VT will be decreasing, yeah? Because this is going up while VT is constant, and therefore VT will be decreasing. and this means that Vt is decreasing as we increase the load, yeah, or as we increase IL. And therefore, if you look at on the left hand side on the top diagram or the top plot, you can see that EA is constant, yeah, while Vt, as you go from the left to the right, Vt is decreasing, okay? So as IL is increased, Vt is decreasing, yeah? Vt is coming down, okay, right, and then it's decreasing linearly, as you can see, yeah? From the plot, the first plot, yeah? Plot A. Now that would be the terminal characteristic of this DC generator when armature reaction doesn't exist, or we assume that armature reaction didn't exist. But when armature reaction is present, then it will have effects on the Vt, yeah? How does it affect the Vt? We know that the armature reaction causes flux weakening, yeah? Flux weakening, it means that as the armature reaction getting worse, or it's getting bigger, getting more significant, the flux will be getting lower and lower, yeah? And the armature reaction getting worse as the load is increased. When the load is increased, the armature current is increased, and therefore the armature reaction getting worse, i.e. it's getting more significant. Okay, again, so if I write it down, as the load is increased, IL, yeah, is increased as well, which means that IA for this type of generator is increased, and therefore AR is getting more significant, the armature reaction, and therefore it will result in the decrease in the flux, yeah? Because of the flux weakening, yeah? Right, so the flux is getting less, as you can see from there. Then it will have an effect on the EA, which is that EA is getting lower and lower as well, yeah? Okay, so as we increase the load, EA is getting lower, and that's why if you now look at the second plot, the one on the bottom there on the left hand side, as we increase the load, EA actually drops, yeah? It's not constant anymore, yeah? There is this AR drop here actually affecting the EA, and therefore now what we have is no longer this line here, but instead we have this curved line of Vt, yeah? And if you compare the second plot with the first plot, the Vt is actually lower than before, yeah? The Vt on the second plot is lower than the Vt on the first plot, and the drop is getting will be larger when the load is larger. Okay, so this is the terminal characteristics of the DC generator when armature reaction is present, yeah? If the armature reaction is not there, then we have the first plot as the terminal characteristic of this separately excited DC generator. Okay, now on this slide we're going to see the control of the terminal voltage. And again, if you compare against the motors, we did talk about control of the speed, yeah? But when it comes to generator, the output is this terminal voltage, and then so the question is, how do we control it? For example, the load may change, but you don't want the output voltage to change, so you want to control it. You want to control the output voltage. You want to control the terminal voltage. So how do we do that? Right, VT, or the terminal voltage, can be controlled by changing the internal generated voltage EA. Yeah? So to control VT, we control the EA. Okay, the internal generated voltage. Right. Okay, and then there are two ways to do this. Yeah. First is by changing the speed of the rotation, and second is by changing the field current. Okay, and from this equivalent circuit that we've seen before, we found that EA is equal to VT plus IA RA. Okay? And also another equation for EA that we know that is EA is equal to K pi omega M. Yeah. EA equals to K pi omega M. Okay, that's why when we want to control VT, we can achieve it by changing EA. And then how do we change EA? How do we adjust EA? We can see the second equation here, that we can achieve it by changing either the flux or the speed. Yeah. We cannot change the K because K is constant, and it's just depends on the design of the machine. Yeah. So again, there are two ways of adjusting EA, i.e. by changing the flux or by changing the speed of the generator. Okay, right. So for the first method, changing the speed, if you look at the left hand side here, if we increase omega M, yeah, then EA will increase, yeah, following the second equation. So if you increase omega M, the EA will be increased, and therefore VT will be increased as well. Okay, so if you increase the speed, VT will be increased. That's the second method. Obviously, it's vice versa. If you reduce the speed, then your VT will be reduced as well. Right, and the second method is by changing the field current. And how does this change in the field current affect EA? Well, if you, for example, changing the field current can be done by changing the field resistance. Yeah? If you look at the equivalent circuit diagram, the one that I circle in red here, that is the RF, or the field resistance. Yeah, and if we, for example, reduce this RF, IF will be increased. Yeah, because we know that before that IF is equals to VF over RF. Yeah, so if you reduce RF, IF will be increased, and then when the field current is increased, the flux generated by the field circuit will also be increased. Yeah, the relation between the field current and the flux is given by the magnetization curve. Yeah, so if you remember the magnetization curve, I draw it on the right hand side. The x-axis is MMF, yeah, which is N times IF, and we've got flux on the y-axis. And if you remember that the shape will look like something like this, right? Okay, so we can see that as we increase the MMF, which is the IF, flux will also be increased. Yeah, it's quite linearly, especially in the within the linear region here. Over here in the saturation region, flux is still increased, but not as much as it was in the linear region. Okay, and therefore again the second bullet point, the second method here, as IF is increased, flux will also be increased. Yeah. And then if you look at the second equation again on the right hand side, as the flux is increased, we can see that EA will also be increased. Yeah. And when EA is increased, VT will also be increased. And therefore, as the summary, if we reduce RF, the VT will be higher, and vice versa. If we increase RF, VT will be decreased. Okay, so that's how we do the control of terminal voltage of this type of DC generator. Okay, the second plot here, plot B, basically shows us the effect of reducing the RF. So if you look at the here, R2, which is this one, is less than RF. RF2 is less than RF1. So if we start from initially, this is the output, yeah, the VT, how the VT changes against IL. But when we change the RF, when we reduce RF, then the line will be shifted up. Yeah? This is the new one. Yeah? And as you can see here, this agrees what we saw before, that when we reduce RF, the VT will be increased. Yeah? The VT will be increased regardless what is the value of IL. Okay, now we are going to discuss the second type of the DC generator, which is the shunt DC generators. A shunt DC generator supplies its own field current by having its field connected directly across the terminals of the machine. Yeah. So if you look at this equivalent circuit here, we can see that the field circuit, yeah, just this, is connected directly across the terminals of the machine. Okay, so this is the shunt DC generator, and as you can see as well, that it doesn't have a separate or an external voltage source to power up the field circuit, yeah, which is different from the separately excited DC generator we have just discussed before. Okay, now so yeah, the advantage of this generator is that no external power supply is required, and this advantage also shared with other types of DC generators apart from the first one that we discussed before. Yeah. However, there's a question arises here: how does this generator get the initial field flux to start when it is first turned on? Yeah. Okay, this question is about how it gets basically the flux, how it gets the field current. If you remember that EA is equals to K flux omega, yeah, and okay, maybe before we discuss about that, let's go back to the equivalent circuit and derive the equations that are important from this equivalent circuit. From this equivalent circuit, first let's find what is IF. IF is simply where is IF? This is IF, yeah, the field current is equal to VT, yeah, this voltage here, over the resistance, which is RF. So IF is equals to VT over RF. Okay, and then from KCL, Kirchhoff's current law, if you look at this node, yeah, then we've got three currents here, IA, IF, and IL. Okay? And you can see from the direction they are flowing. We can see that IA is equal to IL, the line current, plus the field current. Okay, right. And lastly, if you use KVL, let's find the relation between VT and EA here. EA will be, yeah, this is EA. Here is EA. Will be this voltage, yeah, plus this voltage. Okay, so EA and this voltage here is actually equals to this voltage, yeah? So EA equals to VT plus IA times RA. Okay, so those are the equations that we can derive from this equivalent circuit, and that can be used to do the analysis of these shunt DC generators. Okay, now let's go back to the question that we discussed before. How do we get the initial field flux? Yeah? Why this becomes a question? Okay, if you now look at this equation here, yeah, the one in the middle, EA equals to K flux omega. Yeah. To be able to generate the voltage, we need the flux and the omega and the speed. Yeah? So the speed of the generators comes from the fact that it's driven by a prime mover. So there is a speed there because we've got a prime mover that will supply the mechanical energy into the generator. Yeah? However, then the question is, how about the flux? Where the flux come from? The flux should come from, as we've learned before, that come from the field circuit. Yeah, we need the field current here. But then the question is, how do we get the field current if the EA is 0? Initially, we know that there is no voltage is generated by the DC generator. Okay? And if there's no voltage, there's no EA, there's no VT, or they are 0, so IF will be 0 as well. And yeah, and therefore, yeah, EA will also be 0. Yeah, this is like a circle. So okay, if you're taking this, it means that the generator will not work. It will not generate any voltage. Okay. However, in reality, these generators do actually work. So how do we explain this? How where the flux comes from? So if the generator works, it means that it has the initial flux. Okay. So the explanations is that we have the effect what that is called as the, or what we have as the voltage buildup. The voltage buildup is possible because actually these machines have what is called as the residual flux, or you can say that the poles actually have become magnetized. Although it's not very strong, but there is some magnetic property remaining even after you switch off the machine. Yeah? So even if there is no voltage present, because the poles have been magnetized, there is some remaining flux, yeah, in the system, and this flux is called as the residual flux. The residual flux is not significant, it's quite small, however it's enough to allow us to generate the initial internal generated voltage when the motor or the generator starts rotating. Yeah, again, if you write it down, the equation is EA equals to K flux omega. So we've got a very small flux initially, yeah, which is the residual flux, yeah? But then when the rotor starts rotating, then although initially EA is very small, but EA is there, and when EA is present, when EA is generated, we've got some VT, and therefore we have a field current as well. And the presence of field current, it will generate additional flux, if you like, delta flux, that will add onto the initial flux, i.e. the flux in the system will be increased. Okay, and when the flux of the system is increased, EA will be increased again, VT is increased, IF is increased, and the delta flux will be increased, and therefore the flux will be increased even higher. So this will be go in circles. So the flux will be getting higher and higher, and the EA will also be getting higher and higher. Okay, and the flux getting higher and higher until it's reached into the saturation region, if you like. When it gets saturated, then it will not be increased anymore. So this is what is meant by the voltage buildup. During the increase or the buildup of the flux, the VT will also be increased, and therefore we've got this what is called as the voltage buildup. Okay, so this is the explanation why this shunt DC generator can still work, although initially there is no field current. Okay, that is supplied to the generator. Okay, now how does the terminal characteristic of this shunt DC motor look like, or this shunt DC generator look like? Okay, again, the terminal characteristic of DC generators, basically how the VT, the terminal voltage or the output voltage, changes with load, and the load is represented by the line current, yeah, and or maybe I should say that how the VT changes with IL. These two are the output of the DC generators, which are the voltage and the current. Okay, and again, the equations that we need to derive this, basically the first one is we've learned before that IA, by using the KCL, derive that IA equals to IL plus IF, yeah? And then another one is that EA is equals to VT plus IA RA, and also we know that EA is equals to K plus KI. Right. Okay, now as the load on the generator is increased, yeah, IL will also be increased, and if you remember that when we talk about load is always proportional to the line current IL. So when the load is increased, IL also increase. Yeah, so IL is increased, and therefore IA has to be larger as well. Okay, and this will result, this drop here, yeah, the voltage drop IARA will also be larger, yeah, and the effect is that because assuming this is still constant, VA is still constant, VT will be decreased, it will drop. Okay, and when the VT drops, well, there is another equation that for the field circuit, that IF, yeah, if you look at this equivalent circuit, IF is equals to VT over RF. So when the VT drops, IF will also drop, and we knew already that this will affect the flux in the system. Yeah? So when the IF drops, the flux also drops, and therefore it will also have effects on our internal generated voltage for EA. EA will then be decreased as well. Okay, and yeah, and then the drop in EA will cause a further drop in VT. Yeah? Because this is EA. When EA drops, VT will also be decreased. Yeah? So this is what you're gonna have if you look at the plot. As we increase IL, first this is EA, the first line on the top, the horizontal one. EA initially is constant, but we've got the drop of IARA, which is getting larger and larger, and therefore we've got this line. And then because the flux is also weakening, as we've discussed, because of the drop in the VT, and also because of the armature reaction, then we've got an extra drop here due to the flux, the field weakening, and so therefore we've got this line here. Okay. So this is our terminal characteristic of this shunt DC motor, or shunt DC generator, sorry. Right, and the third statement, the third bullet point, the fourth one, says that the voltage regulation is worse. Remember, voltage regulation is the change in the output voltage, i.e. the difference between the no load voltage, which you can see it's here, with the full load voltage. If you assume this is the full load, yeah, it's over there. So for this shunt DC generator, is worse than the separately excited. Why? Because with the separately excited, the field voltage, yeah, the voltage across the field circuit was constant. It was not affected at all by the load. But now with this shunt DC generator, as the load is increased, the voltage across the field circuit, which is equal to VT, yeah, is actually decreasing. Yeah? So it means that the field current will also be decreased as the load is increased, and that's why the drop in the output voltage with the shunt DC generator is worse than the drop in the VT for the separately excited DC generator. So maybe if we can draw just for a comparison, if we add another one, another line here, just for illustration, this could be the terminal characteristics for the separately excited. So the drop is not as significant as the one that we have for the shunt DC generator. Okay, now we've come to the third type of the DC generator, which is the series DC generator. In this type of the DC generator, the field of series, i.e. the field circuit of the series generator, is connected in series with its armature. You can see from the equivalent circuit here, the field circuit, which is this, is connected in series with the armature. Okay, so they are connected in series, which is different from the shunt, where they are connected in parallel. The series field requires fewer turns of wire to produce the same MMF as the shunt field, because the armature current is high. Okay, let me try to explain a bit more on this. Okay, because the series circuit or the series winding is in series with the armature, it means that we can see from this equivalent circuit that here the field current is represented or is symbolized with IS, rather than IF. But for me, it's just the same thing. You can say, you can use IF or IS. It's the same thing. It's referring to the field current of this DC generator. So for this type of generator, you can see that IF or IS, whichever you use, I would personally use IF, is equal to IA, the armature current, and also equal to IL. So they are all the same, because they are all flowing in the same loop. Okay, so different from the previous case, the shunt DC generator, here the field current actually changes significantly as the load changes, because we know that IL is always proportional to the load. So as the load increase, so basically when the load is increased, when the load is high, IL will also be high, and therefore the IA also high, and IF or IS also will become high, which is very different from the previous type of DC generator. And this means that the field current can be very, very high, and therefore to generate the same MMF, because now IF is so high, to generate the same MMF, you want to reduce the number of turns, and that's why with this type of DC generator, we use fewer number of turns of the wire. Okay, now the next statement, it says that the series field also needs to be designed to have lowest resistance value possible, since full load current flows through it. Okay, now because very full load current, between very high current, flows through the series or the field winding, so it means for the field winding, or the field circuit, yeah, we want to have its resistance, in this case RS or RF, doesn't matter, again whichever you want to use. We want to make this as low as possible, yeah. So how do we achieve it? How do we make the resistance of this circuit low, yeah? We can do this by using a thicker wires, yeah. When the wire is thicker, yeah, by using these thicker wires, when the wires are thicker, it means that the diameter is larger, yeah. The diameter is larger, it means the cross-section area of the wire also larger, yeah. And then we've got the equation that resistance, this is cross-section area, is equals to resistivity times the length of the wire divided by the cross-section area of the wire. So as the cross-section area is higher, the resistance will be lower. Okay, so this is how we achieve having the resistance of the wire as low as possible, i.e. by using wires that are thicker than the one that we normally use for the shunt DC generator, yeah. Okay. Okay, how does the terminal characteristic of this series DC generator look like? Right. At no load, there is no field current. Again, when the load is 0, IL or the line current is also 0, and therefore you can see all these currents will become 0, yeah. IA equal to IS or IF, and also equal to IL. Right, so all these currents are 0, and therefore there is no flux induced by the field current, because the field current, or in this case the series current, is 0. However, as we learned with the previous type of DC generator, that there is a residual flux, yeah? And there is residual flux, and therefore we have some internal generated voltage there, some EA is already generated there, yeah, although there is no flux induced by the field current, because there is no field current. Right, then now as the load is increased, yeah, as we increase the load, IL will increase, yeah. And therefore IF will also increase. Remember, I'm using both here, IF and IS as the same thing, which is referring to the field current. Okay, so as the load is increased, then the current will also be increased. That as the IF is increased, yeah, as the load is increased, IF, the field resistance, also increase, and which means that the flux will be increased as well. And when the flux is increased, the internal generated voltage, yeah, will also be increased, yeah. It is increased significantly as the load is increased, right? But at the same time, the voltage drops, IA times RA plus RS, yeah, will also be increased. If you refer to the this equation here that we can get easily from the equivalent circuit, as the IA is increased, then this voltage drop also will also be increased. Yeah? Okay, which will have an effect on the VT. Yeah? Okay, however, because the general trend EA is increasing, yeah, as we increase the load, you can see here from the dash line, the dash curve on the plot, EA is increasing until actually it starts, the machine starts to become magnetically saturated. At that point, EA will become more or less constant. Yeah, you can see here in this region here. However, at the same time, the voltage drops is not constant. Yeah, as we increase the load, IA will still be increasing, and therefore this voltage drop is also increasing, and therefore, although the EA is constant, VT will start to drop. Yeah, and this is the effect that we see from here, that VT is not constant, but it starts to drop, and so on. And you can see the fourth bullet point says that this generator is not suitable for constant voltage sources. Why? As you can see here, that the variation of VT is so significant when the load is changed. Yeah, and also it's not the VT doesn't change in one direction. Initially it's increasing, and when the machine starts to become saturated magnetically, VT starts to drop. So it's not proportional to the load at all. Yeah? And that's why this type of DC generator, which is series DC generator, is not a good candidate for constant voltage sources.